Hello. We'll wait for 2 more minutes till the people join, at least one or two students. Then we'll start. So I'll start the session now. The students may join meanwhile. Good evening, everyone. I'm Shruti. I'm one of the PMRF NPTEL TAs of the course Ultrafast Laser Spectroscopy. Today is our second live session. We will begin. I hope the slides are visible. So first I'll discuss the weekly assignment 1. The deadline of the assignment was, I think, 8th of February. So I'm sure you must have submitted the assignment. So we'll discuss the assignment today and you guys can correct your answers, or if there is any doubt you can ask me. So the first question was, a laser spectrometer has superior resolution than an ordinary spectrometer because laser light is pulsed, coherent, highly monochromatic, or intense. So it is asking why a laser spectrometer has better resolution. I think this has been discussed in week 1 lecture 1. So we'll first discuss what is the difference between an ordinary light and laser beams. So first point written is, in ordinary light the angular spread is more. Now what is angular spread? What is ordinary light? First of all, you might have seen this torch. Maybe suppose this is a torch. So how the light comes out of the torch? We see like this, it goes, the spread is like this, the beam goes like this, isn't it? It goes in an angular manner. So that's what it is written in ordinary light. Ordinary means unpolarized light in all directions. Hello Ajay. Hello.
Hello, yes ma'am.
Can you hear me properly?
Yes ma'am.
Okay. So have you watched week 1 lectures?
I have no proper idea ma'am, but I am just uh, watching what are going on.
Okay. So I request you to watch the week 1 lectures so that now we are
Okay.
discussing the assignments which have been given. Did you go through the
Oh,
assignments?
okay. No ma'am, I have not solved assignment yet.
Okay. But the assignment for assignment 1, the deadline was 8th February. I don't think you can submit now. But okay, you just attend the session. We are discussing those assignments only today.
Okay, okay ma'am.
Okay. Can you see the screen presentation?
Yes ma'am.
Okay. So in assignment 1, the first question was, a laser spectrometer has superior resolution than an ordinary spectrometer because the laser light is pulsed, coherent, highly monochromatic or intense. So we have to choose one of the options. So now I am discussing what is the difference between a laser light and an ordinary light. Okay. Can you tell what are the examples of ordinary light?
Ordinary light as in uh, monochromatic light. These are.
Ordinary light monochromatic?
I have no idea
Okay.
in this.
No, ordinary light is always polychromatic. Laser lights are monochromatic. Monochromatic
Oh.
means what?
One type of wavelength.
Yes. Single
Hmm.
wavelength or one wavelength.
Single wave.
So
Yes.
ordinary light is a mixture of many wavelengths. For example, our sunlight.
Direct sunlight.
Yes, our torch lights. Okay,
Yes.
these are all examples of ordinary light. Here it is written mercury vapor lamp, sunlight. Okay, so I was
Yes.
discussing the properties of ordinary light. So in ordinary light, the angular spread is more. Now I was telling what is angular spread. So when you turn on a torch, you must have noticed how the beam goes. The beam goes like this, isn't it?
Yes. Spreading.
Yes, it spreads. Like this is the area of torch. Does it go straight?
Yes.
It won't go like this mostly. Mostly it will go like this. So the ordinary light, it gets spread out. Okay, it gets spread out. So that's what it is written.
Yeah.
In ordinary light, the angular spread is more. But what happens to laser beam? Have you seen a laser torch? Laser light, LED. A laser torch you must have seen. We are now getting in market laser torch. The small, it will be like this, and only one. It feels like there is only one ray will go straight. Have you seen anything like this? So in a laser beam, the spread is very less. So wherever you will focus this, it will go directly to that point only. It won't spread like here. This spread is not there. It won't spread like this. There is one beam, it will try to move along in that direction only, maximum possible in that direction. Hello? Okay.
Yes, ma'am.
Okay. I thought you are saying telling something. Okay, so that is the first difference. In ordinary light, we have more angular spread. In laser beam, this spread is very less. And second point is they are not directional. What does
Yeah.
directionality mean? Can you tell?
Direction means, ma'am, it goes here, there.
Yeah, it doesn't has a proper direction. It will go, see, the light was shown in this direction, but it is going here also. So it is the both the points are same. It has angular spread and it is not directional. In it won't go in whatever direction we are showing. It will always have a spread. Okay, but the
Okay,
laser
ma'am.
laser beams are highly directional.
Yes, ma'am.
Yeah, see, we pointed it laser beam. For example, this is x direction, this is y direction. We pointed it in the x direction. It is going in x direction only. It is not going here, there, or here, this side. No. So that's why a laser beam is highly directional. Okay. The third point is it is less intense. Now is intensity and energy. We can say ordinary light will have very less energy. Why less energy? Because again the same thing, it the energy will not, if we are trying to focus this point, the light is spreading out all over. So the energy which we want here will not be that much. Okay, because the light rays are going in this direction also. You got my point, Ajay?
Excuse me, ma'am. I have not gone through the video lecture, so I am not getting well.
It's okay. I think you will be able to follow whatever I'm telling. Okay. These things are not properly taught in the lecture. So I'm just discussing the question so that you can just you may answer the quiz now also, whether you will be able to submit or not, but you just try to attempt the quiz. Okay. Where are you from, Ajay?
I am from Varanasi, ma'am.
Varanasi. Okay.
Yes, ma'am.
And what are you doing nowadays?
Nowadays, I am preparing for NET GATE CSIR exam, ma'am.
Okay,
I
so
have done my MSc 2020.
okay, you have done your MSc. Great. Then I think you will be able to follow the course. Okay. So the third point here was highly intense. Laser beams will be intense. Fourth point is ordinary light. It is not a coherent beam and it is not in phase. Now, what does a coherent light means? Can you think of it? What a coherent light means?
Coherent light. Sir, ma'am, I am not known this top particular.
Okay, so coherent means in phase. Do you know what is phase?
Phase means,
See, for example, there is one beam which is like this, one wave. Okay, so
okay.
and there is one more wave which is like this.
Okay.
So are they in phase or out of phase? You can just tell, because they this is called in phase. They
Then
differ.
what will be out of phase now?
Out of phase will be like this something. If they are like this, here it will be,
Oh,
see, they here
yes.
the maxima, here it is coming minima. Okay, so laser
Yeah.
ordinary lights are not coherent, but in laser beams all the light will be in phase like this. Okay, so maxima comes over maxima, that's why we get intense light. And this we already discussed, that ordinary light is polychromatic, mixture of wavelengths. Okay, and laser light will be monochromatic. So if we'll say we have a laser, we have to specify what wavelength it is. So for example, we have a laser of 405 nanometer. This means it will span, it will be of only 405. Okay, so here we have given some examples: sunlight, mercury vapor lamp, these are all ordinary light. And lasers, there are types of lasers. These are example of gas laser: helium neon laser, HENI laser in short, CO2 carbon dioxide laser. We also have lasers which are solid state lasers. Okay, so
Okay.
the question was, the laser spectrometer has superior resolution. So let me tell little bit, as you have not gone through the course. So in course, sir has discussed, so for example, if you will use an ordinary light to measure a spectra, suppose you are getting something like this. Okay, here is, here some wavelengths are there, lambda 1, lambda 2, lambda 3, and here is intensity. Okay, for example, you are measuring emission. Okay, this is from ordinary light. But when you will use a laser, what will happen? We will be able to, so you can see here, here one hump is there, one hump is here, one hump is here. Okay, so whatever may this compound be, it is supposed to have like three peaks, right, Ajay?
Yes, ma'am.
We can have three peaks here, right? One from, one like
Right.
this, one here, and one here, isn't it? But what is happening, because the light, these wavelengths, for example,
They
this is 405, this is
yes.
407, this is
Four.
409. Okay, because these
Okay.
wavelengths are very close, nanometers. Okay, so this spectrophotometer is not able to resolve this peak. But if we will use a laser light as the source, what will happen? We will get discrete peaks like this. Okay, here this is maybe 405, here 405.5, like this. Okay, so you can see here the wavelength delta lambda is 0.5 nanometer. Okay, and how much here it was? It was 2 nanometer, right? The difference between these two. Okay, So what it is called that here the resolution was more. Sorry, the resolution was less. The resolution was less. And here what happens to resolution? Resolution is more. Ajay? So why here resolution is more? Because here we are able to distinguish two peaks or 2 points which are 0.5 nanometer apart. So that's why here we have more resolution, and this is because of laser source. So the answer here will be the light is highly monochromatic. It won't be intensity, or coherent, because these two things can be, we can manage these two things in ordinary light also. We can make the ordinary light intense and we can make them coherent by adding some polarizer in front of the ordinary light, then it will become coherent, but it still be highly monochromatic. It won't be monochromatic, still it will have many wavelengths. So that's why laser spectrometer has superior resolution. Now here one more point is this pulsed. What is pulsed? What do you mean by pulsed laser? So this whole course is will be about the pulsed lasers and the use of pulsed lasers. So let me discuss about it a little bit. So what happens for a continuous wave laser? This is continuous wave laser. The electric field will oscillate in time like this. This is time and this is electric field. Okay. But in pulsed laser, what it will be, we will have, here we will write intensity and here it is time. What will happen? For some time we will have a laser pulse and then it won't be there. Again, there will be some gap. We will have a pulse and there will be a gap. Again we will get a pulse and there will be a gap. Again we will have a pulse. So what is happening here? Suddenly we are getting some intensity, then zero intensity. Again some intensity at this point, then zero intensity. So these are called pulsed lasers. And this is the laser full width of half maxima, and this is called TR. And what is TR? I'll write here. TR is called repetition rate. Repetition rate means after how much time we are getting another pulse. So we got a pulse at t is equals to 0. So this time will be T0 plus Tr. This time will be T0 plus 2 times Tr. So after how much delay we are getting a pulse, that is called repetition rate. And this is called, this which I have shown inside the pulse, this is called pulse width. Okay. So we will discuss about repetition rates a lot when we move along with the course, maybe in the 5th, 6th week. So there we will discuss more about pulsed lasers. So let's finish the first question. Yeah. Okay. So the second question was, from the theory of chemical dynamics, the fastest possible chemical process is expected to have a rate constant of the order. So I hope you guys must have solved this question. It was discussed in the class, but I solved this here for you for the sake of completeness. Okay, so the formula which we are using here comes from molecular reaction dynamics, called activated complex theory. This is a part of MSc. So MSc people who are attending this course will be able to relate, and for others, it doesn't matter, just you just uh, go through the formula I am giving here. You'll learn it when you will go to MSc, or when you will learn this reaction dynamics course in detail. So here it says the rate constant, this is K, is rate constant, is given by KBT by H, Q star divided by QA, QB, exponential minus EA by RT. Now we'll look at what these terms are. So this K is rate constant of the reaction which we are being asked. This Kb is Boltzmann constant, T is the temperature in Kelvin, H is Planck's constant, and these Q's, these all are partition functions. Partition functions. And this EA is activation energy. So for K to be maximum, this term is whole a constant term. All the terms are constant. For K to be maximum, this whole, all these terms here should go to 1. It should become 1. Okay. And this exponential part, e to the power minus EA by RT, will become 1. When it will become 1? Can you guys tell? So this exponential part will become 1 when we have when we will have EA equals to 0. means activation energy of the reaction will be 0, means it's the barrierless reaction, there is no barrier. So how we know activation energy? We depict like this. This is EA, here is A which is reactant, here is B which is going to be product. This is potential energy on the y-axis, x-axis will be reaction coordinate. So when this cap, this is our activated complex. So when EA will be 0, this whole term will be equal to 1. And we will assume that the potential energy, the partition functions Q star, QA, QB is equals to 1. Because we are doing this because we need the K to be maximum. So that's why these all terms should go to 1. Now what we are left with, rate constant K is equals to KBT by H. Okay, so I don't think temperature is given, so we will just assume room temperature here. You guys assume room temperature because we are just asked the order, so we will take room temperature. Now we'll put the values. Boltzmann constant is how much? It is 1.381 into 10 to the power minus 23. Temperature will be, this will be 300 in Kelvin. Planck's constant will be 6.626 to 10 to the power minus 34. Joule second. Okay, this will be when you will solve this, it will come around 62.52 into 10 to the power 11. So we'll just rearrange a bit. 6.252 into 10 to the power 12. Around 6 into 10 to the power 12. So the maximum possible rate constant will be around 6 into 10 to the power 12 second inverse. So here we are asked order, the order, so here the answer will be fastest possible reaction will have a rate constant of 10 to the power 12 per second. So this is what? 10 to the power fastest possible rate constant at room temperature. Here temperature is important because you can see if we change the temperature, only temperature is the variable. These two are anyway constant. So if we increase the temperature, this may increase. Okay, so no one is around. I hope you guys can check the lectures on YouTube. These sessions are available on YouTube, the recording and the presentation as well. So if you are not attending live, then you can watch the recorded lectures and you can just verify your answers of the assignment. So now the third question was 33% of light incident on a sample is absorbed. Absorbance of the sample is. So it is given that like the sample in the cuvette, we'll draw here. So this is a cuvette, it has some solution. It absorbs 33%, 37%. Absorbs 37%. Okay. So how much is the absorbance? So when we are putting here some light, so the source was of intensity I0 and we will get some transmitted light, call it IT. Okay. Now 37% is absorbed. So how much will come here? It will be IT will be 100 minus 37. That's what. So this is 63%. 63% of I0. We know the formula of absorbance. A is equals to log I by I0. What is the absorbance? It is I0 by I. This is important. You have to keep the intensity of the source in the numerator. I0 by I. So here we will just put the values. This is I0 and this is 0.63 times of I0. That is log 100 divided by 63. That is log. This will come up to 1.587. So the absorbance will you can use calculator to calculate the log. It will come around 0.2. So the sample has an absorbance of 0.2. So here you can keep the answer as 0.2. Okay. Is this fine? If you have doubt in any of the question, you can ask, or you can, as no one is here, you can ask questions even in the discussion forum also. So let's move on to the next question. Yeah, so the question is, for a fluorescent sample and a reference, the emission and absorption parameters are. Here we are given some parameters: sample, reference, absorption at the excitation wavelength AS, AR, intensity of fluorescence, I emission of source and sample. It is just written like this, so it is confusing. I emission of sample, I emission of reference. Okay. Similarly, quantum yield. This is for sample, this is for reference. So we are asked to calculate, to deduce a formula which calculates the quantum yield of the sample, phi of s. So sir has taught this little bit in the course. What is quantum yield? We can start from here. Quantum yield, we need to calculate the quantum yield of sample. fluorescence quantum yield of the sample. Okay, so quantum yield definition is number of photons emitted from the sample divided by how much number of photons it absorbed. So this is number of photons absorbed. Okay, so we can write shorthands as fluorescence quantum yield. Number of photon emitted will be the emission, and it number of photons absorbed will be the intensity of absorption. Okay, this is for our sample. Similarly, for reference, we will have expression like this. Here we will write R now because it is for reference, and intensity of absorption of the reference. So here in this expression, whatever options are given, here we see I emission is there, but there is no I absorbance. So we need to remove I absorbance part from these expressions. Now how we can do that is, we will start from the formula of absorbance. Absorbance is equals to, just now I wrote, log I0 by IT. Now I transmittance, how we can write that? We can write that as I naught minus I absorb, isn't it? As I showed here. Here some light is absorbed, which is I absorbed. Some amount of intensity has been absorbed. So how we wrote IT? It was I naught minus I absorb. This is equals to I naught minus I absorb. So same thing we are using here. Log I0 divided by I0 minus I absorb. We need to calculate this. So we will take anti-log on both sides. Take anti-log. So it will be, since it is a log of 10 to the power base, so we have 10 to the power minus a is equals to I naught minus I absorb divided by I0. Here I just skipped one step. I took anti-log and then did a reciprocal. I'll just write here. So 10 to the power a is equals to I0 minus I absorb. So up when you will take reciprocal, it will be like this. Now divide by I0, it will be 1 minus I absorb divided by I0. So this is equals to 1 minus 10 to the power minus a. Now we are getting closer to the form which are given in options. So here we will get I absorbance is equals to I0 times 1 minus 10 to the power minus absorbance. So this is for sample. We will write SS here. This is for sample. Similarly, we will have for reference same expression. For reference, we will have IR here. How much is the reference absorbing is equals to input intensity 1 minus 10 to the power minus absorbance of reference. Okay, now we can put these two in our equations here. So we will get here when we will write phi sample divided by reference, it will be I emission divided by I absorption of the sample, and for reference when I will write it will become reciprocal divided by I emission of this. Now we have already calculated the intensity of absorbance for the reference and sample. Just we will put it here is equals to I naught times 1 minus 10 to the power minus a for sample into I naught 1 minus 10 to the power minus a of reference. Okay, so here we can cancel out I naught. Now you guys will think how? Because sample and reference we are measuring in the same instrument and all other parameters are same. Okay, so we can just cancel out I naught. Then we will get quantum yield fluorescence of sample is equals to I emission of the sample divided by I emission of the reference 1 minus 10 to the power minus a of reference divided by 1 minus 10 to the power minus a of sample into I have taken the quantum yield of reference here. So this is our expression. So this will be our answer. Answer option number, which option? Option D. Yes. So this is our answer. Now when you will study fluorescence spectroscopy in further detail, we will in this formula we have to include other terms also. For example, we will include refractive index. Refractive index, we will here multiply refractive index of sample whole square divided by refractive index of reference whole square. Why we have to include refractive index? Because we may measure the sample and solvent in sample and reference in different solvents, right? So we have to include this refractive index term also. Now, if we look upon this a little bit more, in this derivation, I just cancelled I0. This we can only do when all the conditions of measurement of emission of sample and reference is same. Okay, and there should not be any error in these measurements. We cannot change the excitation wavelength of sample and we measure in different wavelength for the reference. No, we cannot do that. We cannot change the slit width in between. We cannot change the detectors to measure these two. Then this formula will not become valid. Okay. So in order to use this formula, there are some conditions. Like first one is sample and reference should have similar emission and absorption range. Okay, the sample, for example, if I'll draw here, if this is the absorbance of sample, then our reference should also have some similar uh, absorbance spectra. So if we will excite at this wavelength here, for example, if sample is absorbing here, and at this point we have reference absorbance also, sample absorbance also. So we can use this wavelength to excite both. So that's why the emission and absorption of the sample and reference should have some overlap. Next is they should be of their quantum yields should be similar. So we cannot take a sample which has very less quantum yield and a reference which has very high quantum yield. Then we cannot compare these two. That's why quantum yield should also be in the similar range. And second point, we should try to take the sample and reference in the same solvent. Okay, so that's if you are not using the same solvent, we have to include these refractive index terms. Now I'll just there are some known standards for quantum yield measurement. For example, there is this compound quinine sulfate. It has a quantum yield of 0.546. Then we have fluorescein. It has a quantum yield of 0.95. Then we have rhodamine, rhodamine 6G. You must have heard this name, rhodamine. It, it has a quantum yield of 0.94. So these are few references which we can use for our sample quantum yield measurement. The third point is that instrument settings should be same. Instrument settings should be same. Like as I told, you cannot change the slit width, detectors. So in between we have to keep all the instrument settings same for the sample and for reference as well. Okay, so this was our question number 4th. Here the answer is D. I hope you guys are following and you will match your answers from the recording lecture. Now we'll move to question number 5th. So the 5th question in the assignment asks, usually a modern scanning monochromator contains. Now it is asking about the component in the spectrophotometer called the monochromator. And in the last live session, I had told that monochromator has two parts, slit and grating. But here it is asking a modern monochromator. So here we'll have one more part, which is, as you can see, these mirrors. And these are not plain mirrors. These are curved mirrors. Okay. So to answer this question, it will be a modern scanning monochromator has a grating, it has slits, it has curved mirrors. Now we can just discuss about the working of monochromator here little bit. So what happens in the spectrophotometer, we will have a light source here. The light beam passes and we pass it through some slit and then it hits this mirror and then it is reflected in this way and hits the diffraction grating. Now what happens here at the grating? A grating is an optical component which optical component which disperses the different wavelengths in the incident light to different angles. So here if we are having a light source which has many wavelengths, then it will pass through this curved mirror, it will come hit the diffraction grating, and what happened at the grating, all the individual wavelengths, all the components of this polychromatic light, this is polychromatic, all the components get separate out. So here we are seeing this is blue, this is red part. Okay, so this is the job of a grating. It will just separate out the individual components of the polychromatic light. And then what happens? The separated components come and hit this curved mirror. Here we have two mirrors. This is another curved mirror, and then they will, here one slit should be there. This is also a slit. So now all the components are separate out. So when we will change this grating such that if we want to pass the green light only here through the slit, then we will keep the grating like this. If we want the red light to pass through this, then we can just rotate this grating a bit. Then this light will come and then it can cross the slit. So this is the working of the grating inside the monochromator. It separates the different components and then we can choose which wavelength we want to pass through the slit. Okay, and that wavelength we can use to excite our sample. So here in this diagram you can see we are sending white light, and then we are getting different lights, different components from here. And here we have a little slit, and from that slit here yellow light is passing. If we want to choose violet light, for example, to excite our sample, then we will move this grating, or we will tilt this grating little bit. We'll tilt, and then this violet light will go here. So I'll show from blue ink, this violet light will go here. So this is the working of a grating, diffraction grating. And here what is the principle behind this separation? That is diffraction. So that's why it is called diffraction grating. Diffraction gratings are also two types. One is a reflection type. In the last live session someone asked me this, there are two types, reflection type and then there is transmission type. So in spectrophotometers mostly we are using reflection type. Okay, so this works on the principle of diffraction. Diffraction we all know, we have studied in class 12th physics course, diffraction. So suppose we have here I have an image. See, the grating is like this. This is the surface, and here we have such cuts, and the distance between the two cut is d. So when the incident waveform will come here, it will get reflected like this, like this. And the equation which we are using in the grating is like here. I'm not discussing this equation much. Diffraction equation, because then it will be too much of physics course. Diffraction equation. Okay, so this is about diffraction grating. Here this figure also shows the same thing, that when this light source emits the light, it enters the monochromator. This whole part will be our monochromator part. These are the monochromator part. So when the light source will come here, it will hit a curved mirror, and which will hit from where the light will get reflected, and it will hit the diffraction grating. The grating will separate the wavelengths like lambda 1, lambda 2, lambda 3, and then in the focusing mirror there are two mirrors. This mirror focuses all this light, and then a chosen wavelength, for example here lambda 2, is coming out of the exit slit. If we want to choose lambda 3, then lambda 2 and lambda 1 needs to be blocked. So we will tilt this side or this side, and then lambda 3 will pass through, and lambda 1 and lambda 2 will get blocked. So this is used to select the excitation wavelength. So when we record the absorbance or the emission, like this only we select all the wavelengths. If we want to measure emission from suppose 400 to 700. We are measuring absorbance, for example. In emission spectra, we will keep this excitation fixed. In absorbance, we have to scan the whole range from 400 to 700. So inside the monochromator, what happens? This diffraction grating keeps on rotating and it scans the wavelength from 400 to 700, and then the sample is here. For example, sample is here in this cuvette. It gets excited and then detector collects the absorbance. Again, lambda 3 will come, it will excite, again we will get some point. Similarly, the whole range of wavelength is scanned and then we will get different points and then we will get a spectra like this. Okay, so the question was about modern monochromator. Here the first option is given prism. So as we all know that prism also separates the components of light. So if we have a prism can also do the same job. This is the incident light and the path should be like this, but it will undergo refraction, then dispersion will happen. Here refraction will happen at this interface, again refraction will happen at this interface, and the individual components, it will get separate out. So for example, this is V, violet, indigo, VIB, G, VIB, G, Y, O, R. So the individual component, suppose here we are sending white light, this is prism. Prism will also divide the components like this, and this is, so violet is getting deviated by an angle, suppose theta V, and red light is getting, okay, so this angle is from the original source. So this is theta V and red light is getting dispersed by theta R. These are the two angles. Similarly, we have different angle for all other colors. So, but here what happens that this dispersion is not linear. Not linear. Because the refractive index of this prism itself is wavelength dependent. So, all the colors will not get dispersed by equal extent. Okay. Then the second point is, since this prism is made up of glass, initially we had prisms which are made up of glass, so this also absorbs light. So this also absorbs light. So what happens if we are sending intensity I naught, and we will expect that same intensity I naught should come here also of all the colors, but that won't happen because the prism itself is absorbing. So this intensity transmitted will be always less than I naught. So that's why we are not using prisms in nowadays. Present day monochromators will have grating only, diffraction grating only. Diffraction grating. So if you guys have marked prism also as the answer, then you must have seen that this is a wrong answer for the question. So I told you the reason. The answer will be only these three. Okay. So let's move on to the next question. Now the sixth question is, in order to get a good spectrum, what should be the conditions? It is asking, speed of acquisition should be fast, averaging time should be long, slit width should be small, or concentration should be extremely high. So now we will discuss each point one by one. Now what happens, what is called speed of acquisition? The first thing is speed of acquisition. It is simply called the scan speed. Like how fast, here I told you that the this range is scanned. My pen is doing something. Here I told you that this whole range gets scanned from 400 to 700. So how fast this scanning will go? This is determined by the scan speed or the speed of acquisition. What will happen if we scan very fast? Very fast scan. Like within some 10 seconds, if you will scan, how the spectra will be. So if you will scan fast, what will happen, that it will take this thing is clear, that if we'll scan very fast to complete from 400 to 700 nanometer, we will get very less time, we will take very less time. So fast scan means less time to collect data. To collect data. Okay. But the spectra will become noisy. It will become noisy. Why noisy? Because when you are scanning fast, the detector won't stay at single wavelength for much time to collect the sample absorbance, for example. So we will just get the background noise, which is common for all the wavelengths. The noise is not wavelength dependent. So the data, which is the actual data which the detector has to collect, that counts will get decreased. So the spectra will become noisy. And if you do slow scan here, noise is reduced. Noise is reduced, but slow scan, it will take longer time to collect the data, obviously, because we are scanning each wavelength. We are putting, for example, instead of 10 seconds, we are waiting 30 seconds at one wavelength. And like this, we are doing for all the wavelengths from 400 to 700. So it will take much longer time. to complete data acquisition. Okay, so here I think I have an example which shows this. Yeah, see. So this three spectras are there. These spectras are of baseline. When we want to measure the absorbance of a sample, first what we do, we measure the baseline. So with reference, we measure the baseline. So this is the spectra of a baseline. When the scan speed was very fast, this is very fast. Scan speed was very fast. For example, like we are waiting only 15 seconds at a point, at a wavelength. So we can see how the spectra is not at all smooth. We have so many humps here. When the scan speed was fast, relatively, like slower than the first one, then suppose here we are waiting 45 seconds at one wavelength to collect the data, then here you can compare these two. Here the noise is little reduced, but still it is there, but lesser than the first one. The humps are lesser. And when we keep the scan speed at very slow, like 1 minute, or 1 minute for example, then here you can see we have almost flat baseline. There are very lesser humps as compared to all three. So that's what scan speed means. So if you want to reduce the noise, we have to put the scan speed. We have what? We can keep high or low. So we have to keep the scan speed like this. Slow scanning. Okay. So speed of acquisition should be fast. So this statement is false. Now second is averaging time should be long. Averaging time is also related to speed of acquisition, like the scan speed. Averaging time means when we are waiting 45 seconds at a wavelength, for example 45 seconds at a wavelength, we will collect many readings at that particular wavelength, and then we will average out the readings. So if we are staying for long time at a particular wavelength, we will have higher number of data at that particular wavelength. So higher data will be, so more data means less noise, because we are averaging out at a large number of spectra. We have a large number of spectra, so the noise will get lowered. Okay, so averaging at more, so signal to noise ratio will increase. Now here we have, when we are averaging for a long time, we have more number of readings. Number of reading increases. Number of reading increases. So more values get averaged out, and then we get a smoother spectra. Smoother, less less humps, less humps in the spectra. So that's why averaging time should be long. So this statement is correct. The third one is slit width should be small. Now we have discussed monochromators. Slit width decides which wavelength will pass through the monochromator and will excite the sample. So if we have slit width like this is suppose this distance is 1 nanometer, and here I have a slit width which is like this. So this distance is, for example, 5 nanometer. Okay, so if we want to excite our sample by 540 nanometers, we are trying to pass through here 540. Here also we want to pass through 540, but as here the slit width is large, here it may pass 538 also, 539 also, 540 also, 541 also. Okay, so here we are using 4-5 wavelengths to excite the sample. Sample is kept here. So here, when you are increasing the slit width, the monochromaticity of this excitation light is getting hampered. So when you will keep the slit width lesser, here you may get like 539.5 nanometer, 540 nanometer, 540.5 nanometer. So here the broadness of the wavelength will be lesser. So we should always keep the slit width low. Here I'll write slit width less. But there is also one thing. When you will keep the slit width very small, this is the width, very less amount of light is passing through it. And here we have detector also, D. So the detector is able to detect very small amount of light. But here as the slit width is large amount of light can pass through it. Okay, and detector will detect large amount of light. The counts will be more here. Counts increase. So here noise, signal to noise ratio will decrease because noise is constant in both. Here signal will go down, so signal to noise ratio will go down. Here signal will increase, so signal to noise ratio here increases a little bit, but you won't be able to get the correct spectra here because you are exciting with different wavelengths, but the signal to noise ratio will increase here because as more light is passing through it, the detector will able to detect more amount of light. So there should be a balance between your desired spectra. How do you want the spectra? First, run the sample one times and check how the spectra is coming. So if it is not coming good, the peaks are not coming properly, then reduce the slit width. Or if it is so noisy, then increase the slit width. So you can just play with the slit widths and acquisition time to get the desired spectra. So here I have one example. So this is an example of so this is an absorbance spectra of benzene. Yes, benzene in ethanol. So see, there are three spectras. This red one is at 1 nanometer, 1 nanometer slit width. The blue one is at 2 nanometer slit width, and this black is at 5 nanometer. So when the slit width is large, 5 nanometer, we see there are like there is signature of the peak here, 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 but the peaks are not prominent. It is almost a smooth curve like this. When the slit width was decreased 2 nanometer, we see the peaks have started to emerge out. Different. This is this. So peaks are coming out. When we keep the slit width at 1 nanometer, the peaks are even sharper. This is 1 nanometer. The peaks are getting sharper. So that's why we have to play with the slit width. We cannot keep the slit width very low or very high. We have to check some intermediate range in which we are getting our desired spectra. So we have slit width should be small. Yes, generally the slit width should be small. We cannot keep it very large. Generally we do at 2 nanometer, or if depending upon your sample, if your sample is very emissive, we keep it at 1 nanometer. So this statement is also correct. The fourth one is concentration should be extremely high. This concentration dependence I had discussed in the last week also, last session, that when you will increase the concentration so much, so here we have the absorbance. It should go linearly, but it will deflect. Okay, here we have absorbance, here is the concentration. Beard-Lambert's law say A is equals to epsilon Cl. But up to what concentration this linearity will be there? See, we at very high concentration, very high concentration, this will show deviation. It won't go as a straight line. So we cannot keep the concentration too high. So what happens at high concentration? The solvent molecule will start interacting with themselves. Means they may form dimer, or they can form polymers among themselves. Anything can happen. They can aggregate. So we have to keep the concentration such that there is no interaction among the uh, solute molecule, not solvent, solute molecule. This will be solute molecules. The solute will start interacting. So here we will get, in these case we will get non-linear behavior. So this answers the question that concentration should be extremely high. No, the concentration should be optimal. So the correct answer to this question will be B and C. I hope you guys have done this answer rightly, because sir has discussed these things in the demo video, in the lab demonstration video also. Sir has discussed these things. Now we'll go to the next question. Here, the next question says the fluorescence excitation spectrum does not match absorption spectrum when the sample is. So, and what cases the excitation spectrum will not match the absorbance? So I'll give you the answer. This thing can happen when the sample is impure, or when the sample will have two or more fluorescent molecules, or when the sample will have one species is fluorescent and one is non-fluorescent. So in all these cases we can have an excitation spectrum which is different from the absorbance spectrum. So ideally what should happen? The ideally the excitation spectrum should if it is not overlapping, it should be identical to absorption spectrum, or it should match with the absorption spectrum. So if it is not matching, then we will conclude that either it is the our sample is impure, or there are too many other molecules in the sample, and it can also have that there are some molecules which are fluorescent in the sample and some are non-fluorescent impurities. So these are the reasons when this happens. So here for example I have an spectra here: A, B and C. B is our absorption, B is absorption spectra, C is emission spectra of molecule. I think this is of quinine. These spectra of quinine, quinine molecule. And A is excitation. I hope you guys remember that how we measure the excitation. We will fix the emission, lambda emission, and scan lambda excitation. We scan the excitation wavelength by fixing the emission wavelength, that we want the absorbance at this particular wavelength itself. This is what excitation spectrum means. So by fixing this, for example here by fixing 450, we will fix the 450 in the spectrophotometer, and then we will scan from 250 to 600 or 400 or 450. So if we are choosing emission at 450, we will stop the scan at 445 or 400. This is what excitation spectrum is. So if we have collected the correct emission spectrum, it should also give the correct absorbance from the emission spectrum, which is called the excitation. If it is not giving the identical excitation spectrum, then you can deduce that either your sample is impure or there is something else happening in the sample. Like as sir tells in the video, either your sample is impure or you have a special something special happening in the sample. So in this case here, what is happening? C is our emission spectrum, A and B. A is excitation and B is absorption. So here you can see it is overlapping nicely with the absorption spectrum. Here it is overlapping. But also you will notice that in the absorption spectrum B there are two peaks. Here it is one peak, here it is one peak. There are two peaks. But those two peaks are not very prominent in the excitation spectrum. peaks not clear in excitation spectrum. So can you guys think of a reason why this is happening? Why? We have a match. Of course, the excitation and the emission spectra have overlap. We cannot say the sample is impure. Here, they have an overlap because you can see it is coming exactly at the almost at the same position. But the peaks, there is only one peak. The first peak, which is at lower wavelength, this peak is missing. Peak at lower wavelength is missing. So I'll tell you the reason. This can happen when, suppose this occurs when like there are two isomers in the sample. When only one isomer is emitting, the other one is not emitting. Both the isomers will absorb, but only one is emitting. So that's why occurs mainly from one specific structure which is giving emission. The other one is not giving. Occurs mainly from one specific structure which is giving the emission. Isn't it? So I hope this is clear. So that's how we have to deduce things from the excitation and absorption spectra. And the question was all about this. So the answer, I hope the answer is clear, that when the excitation spectra doesn't match with the absorbance, we can deduce either the sample is impure, or it has two fluorescent species, or it has one fluorescent and one non-fluorescent species. Okay. So let's move on to the next question. So this question number 8, it is about, for steady state fluorometer, a good light source would be. So it is asking, till now we were talking about the source, the excitation light. So from where we get those excitation light? So it is asking what is the source of those light in spectrometers. So for a fluorimeter, it is asking what is a good light source. So I'll give you the range of wavelength which these light sources give. So the first one, this tungsten, it gives around 320 nanometer to 2400 nanometer. Like, then it goes from UV to far IR range. This sodium vapor lamp, this gives this gives single wavelength 589 nanometer. Actually, in principle, it gives two wavelengths which are very closely related. One is 589.0 nanometer, the other is 589.6 nanometer. The third one is deuterium lamp. So deuterium lamp works in less than 400 nanometer regime. From, it will give 180 to 370 nanometer continuous spectra it has in this. And this fourth one, this xenon lamp gives 400 to 700 nanometer. So now you decide that which will be the best to use in our fluorimeter. In fluorimeter, what we do, we excite with the visible spectra and we collect emission mostly in the visible range. Excitation is definitely in the visible range. So the visible range is here. This covers the visible range or the solar spectra. It is closely related to the solar spectra. So we use this xenon lamp. So we use the xenon lamp in spectrophotometer because it has a emission from 400 to 700 nanometers, which is in the visible range. Okay. So I hope the answer is clear. This xenon lamp. So for this question, you should be knowing about what are the ranges of these light source that they are emitting. So these emissions, you can just Google and get these values. So that's how you can answer this question. The ninth question is, a horizontal beam of pulsed laser light is reflected by a retroreflector. In order to bring about a delay of 10 femtosecond in the reflected beam, the retroreflector has to be moved by. Okay, it is asking that when here we have a retroreflector. This type of questions I had discussed in the last session also. So I'm sure you have done it correctly. So this is a retroreflector. It is movable. This is movable. So we can bring it front and back. So it will hit this light and this light will get reflected from this surface and then trace back its path here. So it is asking how much we have to move this in order to get the delay of 10 femtoseconds. Like the path length, the time taken by the light to hit the retroreflector and come back should be 10 femtoseconds. So to start with, we should always remember that light travels 1 foot 30 centimeter in 1 nanosecond. So we have to find how much it will travel in 10 femtoseconds. So 1 nanosecond, it travels 30 centimeter, that is 10 to the power minus 9 second is equivalent to 30 into 10 to the power minus 2 meters. So from here we can get 1 second is equivalent to 30 into 10 to the power minus 2 meter divided by 10 to the power minus 9. So we can time taken, oh sorry, we are calculating distance. So distance traveled by light in 10 femtoseconds will be 30 into 10 to the power minus 2 meter divided by 10 to the power minus 9 seconds into 10 to the power minus 15 seconds, because into 10 because 1 femtosecond is 10 to the power minus 15 seconds. So 10 femtoseconds, I have multiplied it by 10. So this will come up to 30 into 10, 300, and the power will become minus 17 plus 9 minus 8 meter. That is, it will come around 3 into 10 to the power minus 6 meter, which is 3 microns, 3 micrometer. So you guys must have ticked the answer as 3 micrometer. This is given, but this is the wrong answer. The correct answer will be 1.5 microns only. Why? Because we have to consider both ways, going, hitting the retroreflector and then coming back. This should happen in 10 femtoseconds. If we will move by 3 micron, it will take like 20 femtoseconds, maybe double the time. But no, we have to move the retroreflect. We have to calculate the delay in going and hitting and then coming back also. So we have to move the retroreflector by half, because there is the distance s and s. So this 3 micron, this 3, this is 2s. 2s is 3 micron. So s will be 3 by 2. That is 1.5 microns only. So the retroreflector has to be moved. This has to be moved this side by 1.5 microns. That's why this will be the correct answer. Okay. So I hope this question is clear. If you guys have any doubt, you can post in the discussion forum. So let's move to the last question of the assignment, the 10th question. It says, in their electronically excited state, generally, organic acid becomes stronger, organic bases become weaker, or organic acids become weaker, organic bases become stronger, or both become stronger or both become weaker. So this was discussed in lecture 5 in the excited state processes. So what happens? I'll tell you. This is answer is both organic acids and bases become stronger in excited state. They both become stronger in excited state. So how it happens? Let's discuss them one by one. First, we'll take one organic acid example. Suppose this same example I'll take so that it will become much clear. Sir has talked about phenol. Okay, so this is phenol. And this is phenol in its ground state. It will have the energy levels like this. So this is the energy level of the benzene ring in the ground state. We have 6 pi electron. 1, 2, 3, 4, 5, 6. So here 1, 2, 3, 4, 5, 6. These are bonding, these are anti-bonding. When it will lose the proton, it is an acid, so it has to release proton. It will become this phenoxide ion. It is becoming an ion. Now how will the energy level will be? Like this. Now we have one extra electron. which the oxygen has, and it has to delocalize over here, over the benzene ring. So when it is in ground state, the extra electron will come here because these are already filled. I'll denote this extra electron with this green pen. So when the molecule is in ground state, this is the ground state. In the ground state, the extra electron will come over here in the antibonding orbital. This is pi star. But when the molecule will be in the excited state, here I will draw the excited state, 1, 2, 3, 4, 5, 6. This is excited state. So this electron has jumped from here to here. So this is now an excited state of this molecule. Now when this extra electron from oxygen, this electron will delocalize, this electron will delocalize here in the pi, which is of lower energy. Okay, so this delocalization is putting this extra electron in a lower energy orbital. That's why this process is more favorable. So in excited state, this will have more tendency, the phenol molecule will have more tendency to release its proton because the phenoxide ion is getting destabilized in the pi, lower energy orbital. Then in case of ground state, it was getting delocalized in pi star, which is a higher energy orbital. So that's why in case of organic acids, we can say that in excited state, organic acids become stronger acid than what was their tendency in the ground state. Okay, so similarly, let's discuss the organic base also quickly. Now bases, we can take an example of carboxylate. So here again I am taking a benzene ring and it has a carboxylate. Let me draw the energy levels in ground state and excited state. This is ground state and this is excited state. So this level is pi star, this level is pi. This is antibonding, this is antibonding, this is, I'll simply write as antibonding bonding. It is easier, antibonding, this is antibonding, this is also antibonding. So this is a base. It has a tendency to transfer this extra electron to a proton. Okay, means it has a tendency to accept this proton. This electron has to go to a proton. So in this case, the HOMO is a bonding orbital. This is HOMO is a bonding orbital, and here this is a antibonding orbital. So as we know that the electron can be lost from an antibonding orbital more easily than from a bonding orbital. So this can be given to a proton much easier. much easily in excited state than in the ground state. Okay, so similarly here, as we discussed in the case of acids, so here also bases become stronger bases in excited state. Okay, so this is the answer for this question. This was the last question, that both organic acids and organic bases become stronger in the excited state, in the electronically excited state. From where we are comparing, we are comparing from their ground state acidity and basicity. With respect to the ground state, when the molecule goes to the excited state, it becomes more stronger acid and bases. So for acid, what will happen? The pKa, here I will write, the pKa of ground state will be more than the pKa of excited state. So if two acids are there, one is more acidic and one is less acidic. So the more acidic one will have lower pKa. So this, in excited state, the molecules are more acidic, so they have a lower pKa. Okay, same concept applies to the bases also. So here we have come to an end of our session. This was weekly assignment 2 which I have discussed. I hope all the answers are clear to you. And here I have one extra question. If you guys are watching the recording, please do solve this question on your own and let me know the answer in the discussion forum. This is the same question which I have just discussed from the assignment, just I have changed some values. You try to solve this. Calculate the theoretically expected value for the rate constant of the fastest possible chemical process at 1000 Kelvin given the values of the Planck constant and Boltzmann constant are this and this. So this way I discussed in the session. So I hope you will be able to solve this and just write in the discussion forum that you just need to mention the order of rate constant, that what happens to the order of rate constant when we are changing the temperature. Here we have increased the temperature to 1000 Kelvin. It is not anymore the room temperature. So just solve and check what is the order now. Okay. So I will end the session. I hope you guys have watched the week 1 lectures completely and submitted the assignment. And if there is any doubt, you can write in the discussion forum. The TAs will try to answer it. Okay, we will meet next week again, same time, Friday, to discuss the second assignment. Second assignment deadline was also 8th, but we will discuss the assignment 2 next week. Okay. Okay. So I will end the session.